So welcome to the 2020 Summer Series. My name is Jacob Cohen, and I'm the Chief Scientist at NASA Ames Research Center. When we think of robotic space exploration missions, we often think of missions like autonomous rovers on Mars. But with increased capabilities and capacity, robots are becoming an essential tool to reduce risk and optimize processes with humans in the loop. Today's presentation is entitled, What's the Buzz About Astrobee? It will be given by Ms. Maria Bualat. Ms. Bualat is the group lead of the Intelligent Systems Robotics Groups at NASA Ames Research Center. She received a Bachelor's of Science in Electrical Engineering from Stanford University and a Master's of Science in Electrical Engineering from Santa Clara University. Maria came to Ames in 1987 as a member of the photonics groups before joining the Intelligent Mechanisms Group, now called the Intelligent Robotics Group. She previously served as the Senior Technologist at NASA Headquarters Office of the Chief Technologist, the Acting Deputy Area Lead of the Autonomous Systems and Robotics Technical Area, and the Deputy Group Lead in IRG. She is the author of numerous publications. And with that, please join me in welcoming Ms. Maria Bualat.
Thank you. Good morning. First off, I just want to start off by apologizing in advance. My home office faces a fairly busy street, and so the occasional fire truck or Harley Davidson will go by. So we may get a bit of noise from time to time, and I'm sorry for that. Okay, if we can get my slides up. Here we go. All right, thank you. So I'm going to be talking about a robot that's near and dear to my heart. I worked on it for a very long time, and I'm a proud parent, I would say, seeing this on the space station. So next slide, please. There we go. So Astrobee is a new generation of robotic free flyer that operates inside the International Space Station, and it works together with astronauts. Our project started in late 2014, and we just launched, well, not just launched, but last year in 2019, launched 3 robots to the International Space Station and have begun on-orbit operations. Pictured here is Bumble. It's the first bee that we commissioned on orbit. It's sitting on its docking station, which you see in the background with the AR targets. Next slide, please. So I'm going to start off by giving a little bit of context for Astrobee, including its origins and previous NASA projects. Next slide. The previous generation of robotic free flyers are the Spheres robots, which you see several pictured here. They operated on orbit from 2006 to 2020. And we're one of the most heavily used research facilities on the ISS. Many different groups have used the Spheres as a test bed for research, ranging from systems to deal with dead satellites that you might want to repair, magnetic propulsion, and studying how fuel sloshes in zero-G. However, there are several limitations to Spheres that we really wanted to address with Astrobee. For one, they must have crew supervision at all times for safety reasons. For example, some of the materials are flammable, and so the crew needs to monitor them. Also, for each activity, crew needs to spend quite a bit of time just setting up and tearing down for each experiment. The robots, the Spheres were kept in a locker and needed to be brought out, needed to replace the CO2 canisters that were used for the propulsion, and replace battery packs. And then finally, they were only able to operate within a 2 meter by 2 meter by 2 meter volume on the space station because they navigate using beacons, ultrasonic beacons. And so those were tough to move around. And so really these could only operate in that limited volume. Also, after over a decade on orbit, they really began to show their age. The onboard processing is extremely limited. It's like 2004 technology. Also, things like the nozzles were starting to fail. So it really was time for an upgrade. Next slide, please. So Astrobee, which we see here with astronaut Anne McLean, is designed to overcome these main limitations of spheres and also to add a wide range of new capabilities. So here we see Anne McLean, who unpacked Bumble on April 30th, 2019. We checked out a second Astrobee, Honey, in November last year, and we've now passed a year of on-orbit operations. Next slide, please. Besides spheres, there have been some other free flyers in the past that have been given us inspiration and lessons learned. We see in the upper left AirCam Sprint, which was actually an EVA, an extravehicular free flyer that was deployed from the shuttle cargo bay and joysticked by an astronaut. In the lower left, we see PSA, the Personal Satellite Assistant, designed and built at Ames. And it had actually a lot of the same goals as Astrobee of providing an assistant for astronauts. However, it did not quite get to flight. So, but there were some pretty advanced prototypes built of that. And actually several team members from that PSA team ended up on the Astrobee development team. And then finally, on the right-hand side, again, on spheres, we actually flew an experiment where we launched a smartphone to give spheres an upgrade in processing and sensing, and did some of the proof of concepts for Astrobee. Next slide, please. Some other previous intravehicular robots we see here. I already mentioned spheres. Also, JAXA flew this really adorable little ball here in the lower right-hand corner called IntBall. It's a free-flying camera system and very small size, use their miniaturized all-in-one CPU, IMU, and reaction wheel module. And we are actually doing some joint activities with the IntBall team using Astrobee and IntBall. They are actually working on an upgrade, IntBall 2. I'm not sure what the launch schedule is for that. Also not pictured here is Simon. Some people may have heard of. It's a AI-powered free flyer and uses voice interfaces. There's a somewhat famous video of Simon having its feelings hurt when talking to one of the astronauts, but there is an upgrade to Simon. Simon 2 was actually launched late last year, and it uses Watson Tone Analyzer, improved localization, and more sensitive mics. Next slide, please. And then we can go on to the next. Okay, so the goals of the Astrobee project were to deliver 3 free-flying robots and a docking station to ISS to replace the spheres. The main purpose of spheres was to host guest science on space stations. So the primary purpose for Astrobee is the same, and it's to enable guest science. And so we've added some additional capabilities and some interfaces to make it easy for guest scientists to fly their payloads on Astrobee. Also, we have a goal of demonstrating the feasibility of intravehicular robot caretaking for future human exploration vehicles, for instance, Gateway, and to provide an opportunity for future automation of ISS operations, for instance, monitoring crew activities, conducting sensor surveys, basically trying to take care of some of the chores of astronauts on board the space station. Next, excuse me, next slide. Okay, so the technical approach, we used the lessons learned from spheres to inform the objectives for the Astrobee design. So for instance, we want to minimize the burden on astronauts by executing most of our experiments completely autonomously using ground supervision. So we want to use up as little crew time as possible. As I mentioned, spheres had a lot of setup and teardown time and had to be supervised. So we wanted to be have Astrobee supervised by the ground and not by crew on space station. Also, we went with a battery-powered propulsion system and autonomous docking for recharge, so that we don't have to have crew support to resupply our consumables. We incorporate a lot of safety controls, such as collision mitigation and use of non-flammable materials. And we use a vision-based navigation system so that we don't require any new infrastructure for the ISS interior. And this really opened up the whole of the US orbital segment for Astrobee to fly in. Next slide, please. Okay, so I have a little video here. This is a little bit of our history of Astrobee, from initial prototypes on up through our certification unit. So the first 4 years of our development, you can see some of the early concepts of propulsion. This is now our newer propulsion concept we're seeing here. This is Astrobee flying around on our granite table. This is a lab that we have at Ames. We refer to it as an upside down air hockey table. So instead of the air coming out of the table, the air comes out of the puck and allows us to have frictionless motion, or nearly frictionless motion, depending on how clean the table is, to test out some of our technologies. Here we see some of the software involved in the Astrobee project, some of the simulators and control station. We can simulate ISS here. See Astrobee undocking and flying around. We've also already started some testing with some new payloads, with guest science payloads. For instance, we had a Gecko gripper from Stanford. Here we're testing having an external mass that's shifting the center of mass of the robot, and having the navigation system deal with that. Here we see some docking, autonomous docking. And then finally, just an artist concept of how we envisioned Astrobee working on the space station. Okay, next slide, please. So I'm going to now go through some of the major subsystems of Astrobee, and then I'll go into a little more depth on some of the enabling technologies, such as propulsion, visual navigation, and human-robot interaction. Next slide, please. So what we see here are the elements of the Astrobee system. These are the operational system elements. We have the 3 onboard free flyers, and the docking station, which I showed you earlier. Also, we have a ground data system that includes a control station for operators, and some additional servers and tools, engineering tools that enable us to operate the robot. So in addition to these flight elements, we also have some ground testing systems and labs. Next slide, please. Okay, so there's a lot on this slide. I'm not going to go through every little detail here on the parts of the robot. I will point out, I mentioned that we really wanted to enable guest science on the robot, and so we have some open areas that are the payload bays. So at the bottom of the robot, and also the top where we currently see the arm installed, that arm is removable, and we can put in guest science payloads into that slot. See some other things of note. I'll talk more about the propulsion systems later. So Astrobee is basically a sandwich with 2 propulsion systems on either side of a central avionics component. The avionics, there's 3 smartphone computers. I'll talk more about that later. And then the main sensor packages, the built-in sensor packages, which are primarily imagers. Okay, next slide, please. The way that Astrobee communicates is through the built-in ISS Wi-Fi when we're flying. And we have a single telemetry and video stream to the ground. We are able to connect to Astrobee from multiple ground stations. So when we're flying, we're on Wi-Fi. When we're docked, we actually have a Ethernet connection to the LAN. And then if we need to stage large file transfers, for instance, if we had a really long sortie where We had the camera running the whole time, and might have a lot of data that we need to downlink to the ground. We can stage that either to some storage that's on the dock or to the ISS NAS storage. Then we go down through the KU band, through Marshall to Ames, where we have our data archive. And then we've already demonstrated that we can run the robot from multiple institutions. With COVID-19, we've actually been running the robot from the pilot's home. So we're proving that out, that the communications here works. Onboard communication between processes on the robot is using the ROS operating system. It's a robot operating system. It's a fairly common system used widely in the robotics research community. And then communication to the ground is through the DDS protocol. It's data distribution service. And that allows us to adjust quality of service settings. Next slide, please. So onboard processing, I mentioned 3 cell phone class processors. We have them layered to provide some isolation between the software on board. The lowest level processor is a WAN board. It's running Linux. And this is where most of the high rate control software is running. For instance, the power system controls. And then at the mid-level process, where really most of the infrastructure heavy lifting is done with the machine vision. And that's an Inforce board, also running Linux. And then finally, we have the high-level processor that's running Android. And this is where we expect most guest science processes to run. They would be written in Java. It also controls a few of the HRI interfaces, for instance, the touchscreen interaction. And then scattered throughout the robot are microcontrollers for controlling the power management, the propulsion modules, the perching arm, etc. And those are PIC microcontrollers. Let's see, next slide, please. The perching arm, which I showed you earlier in the overview, is designed to grasp handrails. With the concept behind it is that we would perch to save energy. So we would grab hold of the handrails that are scattered throughout the ISS. It's the way that astronauts propel themselves around the station. And once we grasp a handrail, we can turn off the propulsion system and dwell in a place for a long period of time without using too much energy. It can act as a pan tilt once it's attached to a handrail. So the joints of the arm that are used to deploy it can also be used to move the body. There's a forward-facing high-definition camera that we can use to image crew activities. It's also can be used manually, so crew can manually deploy it and attach to a handrail, and this is good for getting the robot out of the way in case of an emergency, so you don't have the robot getting in the way of crew. The end effector, the gripper here that is purposely designed for handrails, can actually be interchanged with other grippers. So for instance, Stanford has developed a gecko-inspired gripper. I showed some of that in the video earlier. That's actually launched and is currently on station. We haven't tested it yet, but crew can just simply unscrew two captured screws here and replace the handrail gripper with the the gecko gripper. Next slide. Here we see the dock again. We have 2 berths on the dock that allow us to communicate and charge 2 robots. There are 3 on board, so the third one has to live in a stowage locker. So if we ever want to have 3 robot operations, crew will need to go and grab that robot and put in some fresh batteries. But generally, we can turn Astrobees on and off remotely through the dock and autonomously dock to recharge as the batteries start to drop. There are magnets inside each of these berths, and that holds the Astrobee to the berth when we're not flying. And when Astrobee wants to fly away, it commands the dock to retract the magnets and that then allows the low low thrust propulsion to pull away from the dock. We have a flexible mounting system. It was very difficult for us to find a home for the dock on ISS. ISS is very crowded. It took probably about 2 years for them to find a slot for us. And it moved around, like the ideas of where to put them kind of moved around. And so we had to design a mounting system that was very flexible, that could deal with different types of mounting fixtures. And so we can actually move the dock around to other places. Next slide, please. So the basic ConOps for Astrobee is that when it's idle, it would just sit on the dock and charge. So that's true for 2 of the robots, as I mentioned. The third would need to be pulled out of stowage. Astrobees can execute complex plans with full autonomy, supervised by the ground, but with no need for astronauts. So this includes undocking, moving to different modules. Currently, though, we only have a map for the GEM, the Japanese Experiment Module, and then returning to the dock. As I mentioned, the Astrobees run with ground oversight. If it encounters an anomaly, say an unexpected obstacle, it will stop and wait for operator intervention. And this is primarily because of scope of the project. We certainly have the infrastructure to do more fault handling on board, but the current behavior that's programmed in is to wait for operator intervention. Astrobee can continue to operate through comm outages. For instance, there are multiple handovers between TDRS satellites, usually during an operation. We've operated Astrobee for on the order of 3 to 4 hours at a time, and you can see multiple handovers during that time, along with some longer LOSs. If we have Astrobee executing a plan, it will continue to do so through that comm outage. And then if it does encounter an anomaly, again, it'll stop and wait for AOS to have the ground supervisor tell it what to do. An operator can always take over from an executing plan, and teleoperate. And astronauts can be operators. We expect this to be a very rare occurrence. The whole idea behind Astrobee was to minimize crew time. However, we envision that perhaps future HRI researchers might want to interact more with crew, and they might want crew to operate Astrobee. So the capability is there. Next slide, please. The hardware status, as I mentioned, all our on-orbit hardware is on ISS. We've launched 3 Astrobees, the docking station, a few spare parts, a bunch of batteries, basically 2 sets per robot. So the robots operate on 4 batteries, and we launched 8 per. In addition to all this flight hardware that's on orbit, we also have 2 flight spares that are currently at JSC bonded stores. So we've got both a spare B and a spare dock. We also have some ground free flyers. We have 2 current ground free flyers that we use for testing at Ames in the Granite Lab. And we also have a ground dock and lots of spare parts. So we did buy a lot of flight spare parts. We purchased enough to build 10 units. And so far we've assembled 6, so we've got some spares there. Next slide. This will just be a quick one, just for an overview. Next slide after that. Okay, so the propulsion system, it's a all-electric propulsion, and this was to simplify the recharge. So we did look at some other propulsion concepts. For instance, Spheres uses a cold gas, CO2 canisters. But we really wanted to simplify the recharge. The propulsion modules are interchangeable. So it's nice because if we have 1 spare propulsion module on orbit, we can use it to replace any propulsion module on any Astrobee. So that was very convenient. It works on 2 or it has a central impeller. My next slide will show you the interior of this, but has a central impeller that pulls in cabin air and lightly pressurizes the plenum. And those impellers counter-rotate to cancel torque. Our max acceleration is 10 centimeters per second squared. Because we are flying around with crew, we have to worry about injuring them, and so all moving parts are enclosed. For instance, the impeller is behind that central screen there. It's a very fine screen because that's the intake. We had to put a fine screen in to prevent astronaut hair from being pulled. And then you can see sort of a grill on either side of that. Those are two of the nozzles. Those grills are sized to keep astronaut fingers out because, as I'll show you later, there's some flappers that could pinch fingers. Okay, so next slide, please. So this is the interior with the cover removed of that propulsion module. I mentioned the plenum. The central impeller draws that air in through the intake. The pressure is very low. It's only 0.1 psi over the ambient cabin air. This was very important. This is a great safety argument. It's a very safe system. Air flows out through 6 nozzles per prop module. So 1 on each of the short faces and 2 on the top face. So we have 12 nozzles in all on the robot. And this gives us holonomic control. I already mentioned the canceling drag torque, so we can move on to the next slide. So these are how the nozzles work. In the lower right, you can see the various states of the nozzles. It's actually a continuous range that we can open those flappers. The air is very slightly shaped. The flow is very slightly shaped by these grills. Excuse me. The air is blown in a fixed direction. And the great thing about this is, of course, that we have unlimited propellant mass. So we really don't have to worry about the efficiency of the thrusters because we have so much mass. What we're most concerned about actually is more power efficiency. And so with the low plenum pressure, we have a very, very high power efficiency. Okay, next slide, please. So this is how we achieve holonomic control. So the thrust vectors for each of the nozzles do not pass through the robot center of mass. So in order to get a pure force along an axis or a pure torque, we have to operate 2 nozzles. We use matched pairs. We do have non-symmetrical performance. Because most of the sensors are in the forward and aft faces of the robot, our preferred direction of flight is forward and aft. There's a hazard avoidance camera in the front. So that's the way we like to face when we're flying. But if we know that it's clear on the sides of the robot, we can fly in any direction. Let's see, next slide, please. Okay, so earlier on, I talked about the limitation that spheres had of having to fly in a small volume in a single module on ISS because of the need for ultrasonic beacons. So we designed Astrobee so that it wouldn't require that additional infrastructure to navigate. And so that would give us a lower impact on station operations and open up the whole USOS to Astrobee. All we need to do is build maps of the interior. Next slide. Here are the external sensors of the robots. The forward-facing cameras. We have a navigational camera, and this is used for our general purpose navigation. Excuse me. There is a matching dock cam on the aft face that we use for docking, hence the name, that uses a fiducial relative tracking for us to mate with the dock. Then we have 2 time-of-flight cameras. Again, a forward-facing HAZ cam that looks for obstacles as we fly, and then on the aft face, what we call the perch cam that is used for handrail relative localization. We have an upward facing camera called the speed cam, and it's a redundant sensor that monitors Astrobee's speed. Oops. Sorry, just clicked on something accidentally here on my laptop. So it monitors the Astrobee speed and will cut off the propulsion systems if it exceeds that threshold. And then finally, we have a forward-facing high-def camera that we use for streaming video to the ground called the side cam. Okay, next slide, please. So for our position estimation, so all the modes that we have on board, which we have 3 modes that we operate in, use an augmented state extended Kalman filter. Kalman filter integrates sensor data to create a state estimate. And it integrates the gyroscope and the accelerometer from the IMU at all times. And then depending on which mode we're in, it uses different cameras. So for instance, for the general purpose localization, this is what we would use throughout the ISS. It does not require any infrastructure. We use a 2 Hertz visual navigation system. And we're getting approximately 5 centimeters of accuracy, I'd say generally using that system. However, we do see increased performance in areas that are feature rich. I'll be talking a little bit more about the localization technology in a minute. So where we discuss the features. So we do actually see even 1 to 2 centimeter accuracy on the general purpose navigation. We also at the same time run a 6 Hertz optical flow system. And this actually allows us to continue to navigate even when we're in an area with poor map data. We have a fiducial relative system. This is used in the vicinity of the dock. And this uses that rear-facing dock cam. You may have noticed earlier on the dock there were some AR targets on it, and so we use that as fiducials to give us this high accuracy 1 centimeter navigation to be able to mate with those birds. We can also put fiducials up in other areas of the space station. We could ask crew to do that, and that would give us again increased accuracy, increased performance for the nav system. And then finally, we have a perch relative mode that uses that 3D time of flight sensor on the aft, used in the vicinity of handrails, and it looks for 3D features of a handrail in order to localize. And we get about 2 centimeters of accuracy on that. Okay, next slide, please. So the general purpose localization uses offline sparse mapping. We take imagery of the environment and build these maps of features. So what you're seeing here, the one on the right is a sparse map of the Ames Granite Lab. You can see the surface of the granite table here and some of the structures. This used to be where spheres testing was done. So we actually have a frame here that holds the spheres beacons, and you can actually see the structure there. And then we also see here on the left-hand side is a sparse map of the Japanese experiment module that we've taken with Astrobee cameras. So the map is made up of these interest point descriptors and estimates of the locations of those points. Next slide, please. So the way that we build the sparse maps is we collect lots and lots of images from different perspectives. The more perspectives we can get, the better, the more robust the system. And then we detect surf features. Those are speeded up robust features in all the images and match them across image pairs and create tracks of those features that are seen in those multiple images so that we can then triangulate the initial camera pose and create interest point location estimates. We see here an example of some visual features in the Granite Lab. Next slide. We then simultaneously solve for 3D positions of those tracked features using incremental bundle adjustment, and then adjust the map to remove, using global bundle adjustment to remove the outliers. We rebuild it using a different type of feature. It's called BRISC, a binary, robust, invariant, scalable key points feature. And then register to a fixed coordinate frame. This is much easier in the lab where we can actually measure where features are. There are a few known features where we have actually been measured on ISS, but not a lot. So, but we are able to register those ISS maps. And then finally, we build a bag of words database that lets us search images quickly. So instead of words as features in the database, we use those features, the images. Next slide, please. So then the way we use the localization is as we're flying, we detect those BRISC features. We look for similar images in the bag of words database. Using ransack, we find a set of inliers and then send that pixel coordinate to the EKF. So similar systems, similar techniques are used for those other modes. For instance, for AR tags, we send the corners to the EKF. For handrails, there are certain handrail features, for instance, the ends of the handrail that are sent to that. And then just for the optical flow features, we're using Lucas Canade with good features to track. And we do backwards tracking to remove the outliers. Next slide, please. Here's just a little bit more detail on the EKF. We use an augmented aerostate EKF that runs at 62.5 hertz. Of course, when we're running those vision processes, the image process takes a lot longer than that. It usually runs at about 1 to 2 hertz. So when the image is captured, a pulse is sent to the EKF that basically marks the point of the image capture. Then while the image is processing, the EKF continues to run using the IMU. And then when the image processing is complete, we do an update step in the EKF. So we basically rewind to that registered point, and this lets the EKF continue to operate at a higher rate. I will say for the state of positioning on board ISS, we are having some difficulties with the localization system currently. We're finding that the ISS is a very dynamic environment, and we're having trouble keeping the robot's map current. So we are looking to upgrade the navigation system to use SLAM, which is a simultaneous localization and mapping algorithms, and that should make the localization more robust to change. Next slide, please. Okay, so human interfaces. We had several high-level goals for our human interfaces for Astrobee. One was to make it very easy to operate. We wanted to have minimal training for ground operators. So when we were developing the requirements for Astrobee, and we discussed with the flight director over at flight operations at JSC, he said that they would not use a system if they needed to certify a new flight controller position. So that's a very expensive proposition, and so we really wanted to make this very easy to use for somebody who wasn't an expert in the system. Also, we wanted to enable future HRI research. So we wanted to provide some basic infrastructure that would let future guest scientists experiment with how a robot could communicate with crew. And then finally, we wanted to be a good crewmate to astronauts. We thought really hard about how crew, who sometimes only have one hand free, could physically interact with the system. So for instance, we looked at hand holds, how they would change batteries, how they would swap payloads, etc. Next slide. So here is our ground data system. We have this Astrobee control station user interface. It has multiple tabs with very various tools that enable monitoring and controlling the robot. We have a sortie planning tool, which sort of see it's pretty small here, but that's what we have pictured here on the right. That lets a user manipulate a model inside of the ISS to set up waypoints and the use of instruments to create a plan for the robot to execute. We also have execution monitoring, so we stream live telemetry. We can have live image and video streams. We have, again, this 3D virtual display that shows the state of the robot. We can run those plans, so we have sort of a VCR type controller. You can press play, pause, skip over steps. And we expect this to typically be used by ground operators. However, we do have a crew control station that is a little bit stripped down. For instance, it doesn't have a planning tool, and it allows them to control the Astrobee in a similar way as the ground controller. We have a server for archiving and distributing the Astrobee data. And we also have some other additional engineering tools that let us, for instance, update software and perform other maintenance tasks. Next slide, please. As I mentioned, we have the crew version of this controller, and we actually have like about a 20-minute training video that is meant to be sufficient to train crew to use the interface. It's actually available online, so if you're at all interested in taking crew training on how to operate the robot, that's available here. You see the link. And we really envisioned sort of these 3 levels of operator capability. The lowest, of course, is the crew. With just 20 minutes of onboard training, they can't plan, but they can run plans, and they can teleoperate and run guest science. The sort of standard operator is somebody who might be a flight controller. They have that sortie planning tool, and then the most capable level is the engineering level, and that there are some additional tabs that give like deeper insight into subsystems, some deeper control into the subsystems of the robot. Next slide, please. We can operate from almost anywhere, and we have been operating from almost anywhere. Anywhere from Johnson Space Center, Marshall, as guest scientists at Ames, or their home institutions. We actually had our first on-orbit activity where the robot was controlled from home back in April. And since then, we've also had JAXA has controlled Astrobee from Japan. And so we're really proving out this system that it can be really controlled from anywhere. We do provide flight controllers with a mobile camera, so they can observe crew activities or do surveys, visual surveys. And we have been operating actually with a minimal crew. The last couple of times we've operated Astrobee, we've had the crew turn a few things on for us, arrange some cameras, but other than that, we've flown the robot without crew supervision. Next slide, please. So the human-robot interaction, as I mentioned, we've put in some infrastructure for that. What you're seeing here is you're seeing on the left is the animation that's run on the touch screen, the eyes that we have there, just to give the robot a little bit of life and personality. Also, each of the robots has a different color and a different name. We have Bumble, Queen, and Honey. And that was really to give the robots a little bit of personality, and so we can distinguish them in videos. We can tell which one is running. We have various indicator lights. We have signal lights. We have indicators about the state of the robot. We also have these audio-video indicators. We have a microphone on the robot. It's not currently enabled, and it's primarily an issue of crew privacy. It turns out crews are more concerned about a live mic than they are about live cameras. So we want them to always know whether or not that mic is on. So you see in the indicators, there's an audio indicator that's blue. We have a similar set of indicators on the aft side, so forward and aft. And then we also will turn a signal light, a single signal light blue on either side of the robot, so that if the crew looks towards the robot, sees blue, they know that there's a mic live. We have a couple of other items on here. We have a laser pointer that lets the robot actually point at things for the crew, some flashlights, and again, the touch screen. Next slide, please. Okay, so this is pretty much finishing up here. This is a video of some of the first operations we had on orbit, commissioning Astrobee. So we see Anne McLean here unwrapping that Bumble. Bumble is blue. So this was very exciting. This is our turn on first wake. You can see the animation, the eyes again. I also find this interesting too, because if you look at the camera, you can see all the pixels that got knocked out by radiation. If you look carefully at the image. Here we see Anne is manually flying the robot through the gem in order to collect imagery to build that first map. So she basically went back and forth across the module with the robot pointing in different directions. Here we attempted to calibrate the IMU. Unfortunately, this is a little too fat. We saturated the IMU. Never ask a former fighter pilot to spin something as fast as they can, because they will. So we ended up having to do that one over again and have them spin it a little bit slower. Here we see some of the first flights. This is our first autonomous undock with David Saint-Jacques. He let us hear the impellers spin up there. That's why he was holding the mic for us. So that was our first time flying off the dock. And then here, David's testing out our disturbance rejection. So he's pushing the robot around, and the robot's job is to stop itself. So we're seeing some success here. Various rotations. And then this was our first autonomous dock. See, so this uses that fiducial relative navigation system. And that green light coming on means we got connectivity. And Christina Cook was very excited. And then she wanted to do some tumbling runs with the robot. So this is her request, to spin the robot and tumble alongside. We didn't have great comms, so there's a little bit of noise there on these images here, this video. Then this is a little bit longer flight. This is still in real flight time. So this is about 10 centimeters a second velocity, or average flying speed. And this is what we envision as being sort of a typical speed. And so from here on, the rest of the video is a little sped up. I showed it like 4 times speeds just so that we can get through some of the sorties, because they're a little bit longer. So then is our first part of our first autonomous flight. So this is now sped up 4 times speed. Christina's job was mainly just to monitor and stay out of the way of the navigational cameras. So she followed along with our flight. And then finally, this was our first autonomous survey. So what we're looking at here is doing a visual survey of a payload rack. So you can see Astrobee here is flying. It's going to fly around the perimeter of the rack using its cameras to take a visual and do a visual inspection of that payload rack. So the propulsion systems have worked great. They've been very capable. So, and I believe that's it. Next slide is just, I think, acknowledgements. Yeah, we were a big team. We were over 60 people. It was built entirely at Ames. It was a collaboration between Code R and Code T, and primarily funded by a game-changing development program, Space Tech Mission Directorate, but also some sort of in-kind funding from the ISS Spheres facility as well. Okay, next slide is, I think, just questions. Yep, there we go.
So thank you very much for an excellent talk, really enjoyable. We have a few questions that I'm going to go through. For those in the audience, please note that we will most likely go a little bit over the 1 hour time frame. You know, as I was looking at the different characters, I was of the different Astrobee vehicles, I was thinking, obviously you had blue light coming in, and the question is, if it goes offline or it changes its mind and refuses the command that you're giving to it, do the eyes become red as a color across there? Always interesting to see how science fiction becomes reality. With that, I'll go into the first question, and I'll give a little bit of an introduction from my perspective on this question. Obviously, when I was in school, I had lots of problems concentrating in little rooms in the library because the fluorescent lights would make noise that would distract me. Space is an isolated scenario, and obviously the station has a lot of noise in it. This first question is, how noisy is it with the fan-based propulsion? How noisy is that fan-based propulsion?
So to qualify to fly on space station, there are limits to how noisy you can be, and it's kind of a sliding scale. You know, there's a maximum noise limit, but there are also, if you're somewhere else on the scale, it determines how long you can operate. So you know, the quieter you are, the longer you're allowed to operate. Astrobee is allowed to, I think when we initially tested it, it was going to be allowed to operate with like full up power to the fan, like the highest rate fans, for about an hour and a half to 2 hours. But we don't operate always at that level. And we did get a waiver because it's not that loud to actually, we can operate Astrobees for the free flyer for up to 8 hours. The dock operates continuously. So it's definitely, you can definitely hear it. In fact, we've actually gotten feedback from the astronauts that they don't feel it's too loud. They've told us that, you know, it's a reasonable amount of noise, and they actually like it because the robot can't sneak up on them. So so in some ways the noise is a feature. So that you know, it's like the Prius is sneaking up on you on the street, right? So they like, the astronauts actually like the fact that they can hear the robot coming. So it's definitely not silent, but and I've heard that the station is a very noisy place. And somebody said it's like having a vacuum cleaner on all the time, something like that. But Astrobee's not that loud.
Yeah, it's really interesting how when you have in close quarters a crew, privacy questions come up. You know, especially when you're looking at the crew and a robot that comes in. I'm going to move on with the next question, and the next question deals with the battery, and more specifically, what kind of battery does the Astrobee use to store charge?
It uses 4 lithium-ion batteries. They're like 14-volt lithium-ion batteries. They are, we put some space between them. Part of the safety story, again, you can't have too large a battery pack, you know, due to fire hazard. But these are certified for use on the ISS.
Okay. And obviously, batteries have always been a question. You know, the question of their laptops and batteries come along the way. The next question obviously comes into the utility of not just being a test for the tool. What are some examples of what the Astrobee can do on the ISS?
Well, so because we have these payload bays, we can accommodate all kinds of different sensors, and some that maybe haven't even been created yet can eventually fly on Astrobee. There are actually, let's see, there's 3 guest science payloads that have already launched to the space station. One is an RFID reader developed by the Johnson Space Center that can be used for logistics. So we can fly Astrobee around. It can take inventory of tagged items on the space station. I don't know how many people know that like stuff gets lost on ISS all the time, and has never known, where it ends up. Some of it is probably already burned up in the atmosphere. So yeah, thousands of things have been lost on ISS, and so part of the plan is to use a free flyer like Astrobee to help with logistics for things like finding lost items, finding tools that crew needs, taking inventories. Another sensor that is already on orbit is a microphone array developed by Astrobee and Bosch. And so they're looking to create sound maps of the interior of the space station. You create a baseline sound map, and then you can look for changes to perhaps diagnose equipment that's starting to malfunction. So start listening for the squeaky wheel. And so that's another experiment that's going to be running soon. And so again, we would do sound surveys of the space station. And we've looked at other instruments that might be used: radiation sensors, CO2 sensors, thermal cameras. So one of the projects that I'm working on now actually looks at using Astrobee to perhaps look for leaks or localized leaks using a sound microphones and thermal cameras to look for listen for the hissing and look for the cold spot where there might be a leak on the space station.
So obviously, we at NASA look to improve the present, but also look to the future. And so following on the ISS question, the next station we're looking at is the Lunar Gateway. And the question is, do you think that robots will be able to maintain the Lunar Gateway during the months when you have non-human presence on the gateway itself?
That's precisely what my current project's looking at, is integrating the vehicle systems of the gateway, or we're testing it on the space station. So we're starting with space station vehicle systems. So integrating those health systems on the vehicle with these intervehicular robots, so that basically the system can monitor using built-in sensors, and then send robots out to either gather more information or to actually enact repairs or maintenance. So yes, that's exactly what we're working on for Gateway.
So as we're looking at the evolution of that interaction between a robot and the humans, the machine itself becomes improved with technologies that we're currently using on the ground. So the next question is Astrobee data available for machine learning researchers to make contributions such as data-driven anomaly detection or neural network-based vision capabilities?
So some of the Astrobee data collected will be, it belongs to the guest scientists, but there is some facility data that's been collected, for instance, the mapping data, and I believe that could be made available. I'm not sure how much currently is. I just should say that I was the project manager for the development of Astrobee, but we've since handed Astrobee over to the facility team, and so they actually are running a lot of this now. So I'm not entirely up on how data is distributed, how much data is being distributed, but yes, I mean, certainly can make an inquiry. I don't think it ended up here. There's a website, the www.nasa.gov/Astrobee is the Astrobee website. And there's a contact information there for the facility. So I don't see why it couldn't be distributed.
And a little bit to add to that for anyone in the audience, not just the person who asked the question, if you do have other questions specific to this type of an approach or scenarios in terms of the technical, we could get you in touch with the right POC to have a more deeper conversation or get information about it. The next question is also a more of a technical question. You know, and I remember part of my work in the background had to do with fruit flies and insects have compound eyes versus our eyes in this scenario. So this question I could relate to. Why are there 3 overlapping cameras on the left and the right?
So each camera has a different use. So I assume you're assuming you mean the front, on the front face. Instead of the in the image, in the picture, it showed it was left and right, but the 3 cameras on the front face each have a different use. And we need them to have similar fields of view. So the navigational camera is used to look for those features so that the robot knows where it is. The HAZ cam is a time of flight camera, so it gives you a 3D point cloud. And that's used to look for obstacles. And then finally, the science camera it's not really used for the onboard flight systems. It's more of a streaming camera that allows somebody on the ground to see it's a high definition camera. So it could be used, for instance, for monitoring crew activities or doing, you know, like a high def or a high resolution visual inspection.
So the last question, and I will again give a little bit of an introduction of my own to the question itself. If you remember back in the days at the beginning, we were talking about workstations that I used and so on. And I remember at that point, we had the desktop computer and you had I think it was a laptop, then a notebook as we're going scenario across there. And during that time, we also had phones that became to be cell phones through Motorola. And obviously right now, we carry things like this, and there could be considered a phone or a portable computer. And so the clear definitions become blurred across as you go forward with the scenarios. So the last question is, what is the defining difference between a machine and a robot? Why does Astrobee qualify as a robot, and did Spheres qualify as a robot?
Well, I think traditionally something is called a robot if it interacted with its environment. Like physically. So, I mean, Astrobee certainly can do that. Without an arm, it can't. We don't touch anything necessarily, but we can install an arm and it can touch. And certainly, I don't know what else I could say about that. Spheres also could be classified as a robot. I think it's kind of a fuzzy, like you're saying, it's a fuzzy line, right? That's like, when does it go from like a satellite to a robot? You know, what's the main difference there? And I think it has to do with like the type of sensing and, you know, the sort of this the type of sensing and interaction that it does with the environment. I think is kind of what makes it a robot.
And I think you know, Issac Asimov, obviously, and I used a quote from him, we used a quote from him, set a lot of standards for robots versus not in science fiction. And of course, that always transition as we develop it. What's really key is to be at that intersection of that fuzzy area. That's where innovation and disruption occurs. This is where NASA thrives, and this is where this work is heading toward in utilization of stations. I do, with that, want to thank you for a great talk. This is the last talk of the summer series. I also want to thank the audience that we had for the summer series. We'll have more talks to come. So thank you very much for an excellent presentation.
You're welcome.